Section: Introduction. In this section, we explore the robustness of transformers to various interventions, particularly focusing on how perturbing activations affects model outputs. We build on previous research to gain insights into the general robustness of transformers. Our approach involves interpolating between different activations in the residual stream after the first layer and measuring the resulting changes in output. Our initial findings indicate that the residual stream of a trained transformer can be divided into stable regions. Within these regions, minor changes in activations result in minimal changes in output. However, at the boundaries of these regions, small changes can lead to significant differences in output. These stable regions develop during training and become more pronounced as the model scales. Models that are randomly initialized do not show these stable regions, but as training progresses or the model size increases, the boundaries become sharper. We observe that these regions correspond to semantic distinctions, with different prompts occupying different regions and leading to varied next token predictions. We note that previous work has analyzed linear regions of neural networks, known as polytopes, but our findings suggest that the stable regions we identify are much larger and do not correspond to semantic differences. Other studies have looked at the robustness of models like GPT-2 by interpolating between activations and noted nonlinear changes in output, which aligns with our observations. To investigate this further, we define a function that represents the forward pass of a transformer with activation patching. This function allows us to replace the residual stream activations after the first layer with interpolated values based on two prompts. We introduce a coefficient that helps us measure the distance between outputs from clean and patched runs. Our experiments involve models with varying parameters, and we compute the distance for multiple values of the interpolation coefficient. We suspect that semantically similar prompts are more likely to belong to the same stable region. To test this, we create pairs of dissimilar and similar prompts. Our results show that for similar prompts, the changes in output are linear throughout the interpolation, while for dissimilar prompts, we observe distinct stable regions with sharp jumps in output. This suggests that activations for dissimilar prompts occupy separate stable regions, while those for similar prompts likely belong to the same region. We also find that the change in output reflects an interpretable change in model predictions, indicating a deeper understanding of how these stable regions function. Section Summary. In this section, we investigate the stability of transformer activations by interpolating between different prompts and measuring the resulting changes in model output. Our findings indicate that semantically similar prompts tend to occupy the same stable regions, leading to minimal output changes, while dissimilar prompts are associated with distinct regions, resulting in significant output differences at their boundaries. Section: Impact of model size. In this section, we aim to determine if our previous results apply to different prompts and models, and if model size influences these outcomes. We sampled 1,000 pairs of unrelated prompts, each consisting of 10 tokens, from the Gutenberg English dataset and applied the same methodology as before. In our figures, we display the median relative distance for various model sizes from the Olmo and Quen 2 families. We notice that the curves become sharper as the model size increases. We further analyze this sharpening effect by plotting the median of the maximum slope of the relative distance, which supports our initial observations. Next, we repeat our experiments, this time focusing on the number of training tokens rather than model size. The results reveal several insights. Initially, the curves for randomly initialized models appear nearly linear. However, as training continues, we see an increase in curve sharpness, similar to what we observed with larger models. This indicates the development and refinement of stable regions during training. Notably, the sharpening effect seems to plateau sooner for the smaller Olmo 1B model compared to the larger Olmo 7B. We identify at least two factors that may contribute to this sharpening. First, models may create additional stable regions, and second, the boundaries between existing regions may become clearer. To explore the second factor, we analyze a two-dimensional slice of the residual stream after the first layer. This slice includes 3 model-generated activations, represented by red, green, and blue circles. We generate synthetic activations within this slice and measure how similar the model's output is to those of A, B, and C. The RGB color of each point in the plot indicates these similarities, with solid colors representing stable regions and color transitions marking the boundaries. Initially, we observe a smooth color gradient, but as training advances, distinct solid color regions form, and the boundaries between them sharpen.